everybody. My name is Melodie Yashar. I'm a space architect. I'm a researcher. I'm starting a new project, and today I want to tell you about some of the conceptual and foundational underpinnings of that project, which coincidentally have a lot to do with analogs. So, what I'm doing and what I'm currently working on is a Mars habitat wall assembly, a technical one, meaning one that can actually be built at scale. And that is exactly what we're intending to do in 2026. We're intending to build this wall system, this wall assembly at scale, and have it be part of an exhibition that will be upcoming and that will be revealed in coming months. And so I want to tell you a little bit about the reasons for the project and why we're doing this, and some of the, again, conceptual underpinnings for this work and how you can get involved if you're interested. So my background is in space architecture, or at least the new emerging field of space architecture, which conceives of how to imagine a future life and work in space, particularly on the moon and Mars. I've been focusing to a great extent on how to autonomously construct habitats within these environments using in situ resources. So I started out, as an architect, really curious and enthusiastic about the potential of autonomous technologies to create habitats and to do large-scale construction. Over time in my career, I became more and more involved with providers in the actual technology development to develop these kinds of systems. And I'd like to tell you a little bit about how that brought me to working on the CHAPEA analog, the Crew Health and Performance Exploration Analog, which is the only 3D printed analog project in the world that's currently operational, and how it has informed some of the underpinnings of the wall assembly project that I'm developing. So a little bit of background, NASA and others have developed a taxonomy of space architecture, which is what you see here. Essentially, they've developed this kind of categorical description of types of vessels, pressure vessels, and which is more descriptive of how they're manufactured and where they're manufactured. So class 1 type space architecture is primarily composed of hard shell vessels, steel, aluminum vessels that are pre-manufactured here on Earth and then launched into space, quite like the ISS was. Class 2 refers to a deployable type of structure, like an inflatable. And Class 3 is an in situ resource utilization constructed habitat. So we're talking about using local materials on the surface of the moon and Mars. Predominantly, we're referring to regolith, and engineering that material and processing that regolith to create high-performance construction materials. There are a couple of processes that we're really interested and excited in for the sake of using in situ materials on Mars when it comes to creating habitats and when it comes to creating various kinds of speak to that in just a second. So a lot of what I've done in my work delivering not only terrestrial, large-scale, additively manufactured structures, but imagining the construction sequence as it would be deployed in space is a lot of building information modeling and construction task sequencing to imagine what the role and responsibility of different robotic agents will be and how exactly humans can stay in the loop and stay informed in supervising those kinds of activities. I'm going to skip this for the sake of time because it's too much natural. So some of my past work has been in response to NASA's 3D printed habitat challenge. 10 years ago, I was part of a team that won not only the first phase of that project, but also the third phase of that project. So we were very successful in this challenge. And it launched an entire career trajectory into thinking about 3D printed habitats, not only in space, but also for how they may be constructed in the short term here terrestrially within the housing market and within the commercial sector. And I'd be happy to speak towards that for anybody who's interested in learning more. So a lot of this had to do, a lot of this work, imagining 3D printed habitats on Mars and the moon, had to do with coordinating, again, a construction sequence that a robot of a certain form factor with certain capabilities could actually execute, and then imagining what the livable space would be for a pioneering crew of 4 or 6, depending on the reference architecture and the mission, and then autonomously construct this with the support of other site support robotics, other robotic agents, and ensure that the habitat is certified for human occupancy. It's no small feat. This is a very ambitious thing, and we're breaking apart the problem in segments, I would say, to address different aspects of this challenge. And it's starting with terrestrial construction. Terrestrial construction is really the best way to approximate construction at scale in the here and now. So some of the things that we've explored in prior projects include the wall assembly of the habitat. What is the primary mechanism by which we're containing pressure so you can live in a short shirt sleeve environment? How are we actually going to work and build with regolith, which is, generally speaking, performs better in compression than it does in tension, so it's not very well suited to containing pressure. How are we going to engineer rebar if we need rebar on Mars? What will that process be? What will the mechanism be? And are there other thermal materials that we need to think about engineering on the surface as well? These are some of the questions that are relevant to designing a habitat system, a wall system that can perform over the long term on Mars. So these, again, are examples of past work, examples of simulations we've created to show how different material systems and also pre-integrated systems like your ECLIS, like windows, like airlocks, etc., can all coordinate within a construction sequence that can factor in contingency when things go wrong, that can factor in autonomous decision-making by robotic agents who may or may not have awareness of what other activities may be at the site. And we're only in the beginnings of this work, but this is, again, to provide some conceptual underpinning for what's to come. There's a couple of leading methodologies for additive manufacturing on Mars. One of them is sintering. This is an example of sintering using lunar regolith, so not Martian regolith by any means, but it's a similar process. You're essentially using directed energy deposition to fuse particles together and to create a tight bond. The other two processes that are currently being considered, or that are, I would say, like, have high applicability for Mars, include geopolymer-based concrete, which geopolymers and alkali activators you may have to bring from Earth. But terrestrially, it's very, very similar to additive manufacturing as we're currently doing it within the housing sector and within other sectors here on Earth. So that's what that looks like. And then the last method that's being considered is sulfur concrete. So basically using local sulfates on Mars to engineer a new kind of heat-based concrete. This brings me to one of the most, I would say, applicable projects that has been completed in recent years, the 3D printing of the Crew Health and Performance Exploration Analog at the Johnson Space Center. We responded to a request for proposal in 2020 to demonstrate that we had the capabilities to 3D print an analog project. And this is the result of being awarded that project, is that we were able to work with NASA to design the habitat itself according to the requirements of the analog. And it's currently in its second mission. The analog is intended to be operational for 3 consecutive missions. The first one concluded last summer. I believe the second one is currently in progress. And 4 crew members lived in this structure for a year. And I haven't, what can I say? We don't have too much data yet. There's not too much published on the results of the analog just yet, but I'm very, very eagerly anticipating what the results of the analog are and what will be shared. Although there is a podcast, it's a good one. So this is how the analog was designed, and the program that was provided in the analog. You have 4 crew quarters, a recreation area, a kitchen area, a workroom, fitness area, robot simulation and communications room, as well as a medical treatment room. You would be surprised how many aspects of this analog's construction we did not have good answers for. We did not have good requirements for. And, it begs the question, are we really prepared? Like, if we can't do this on Earth, can we truly do this in space? And some of those examples I'll speak to, and some of them I'll reference in upcoming slides. So here's the first crew going into the analog, still wearing masks, it being during COVID. And here's a little bit of a before and after of like the design concept for the inside of the analog, which we did not outfit, unfortunately. And this is what it looks like in real life. Here are the crew quarters, and this is the work area of the analog. So it's a 1,700 square foot structure. It's pretty compact. Leaves a lot to be desired in terms of finishing, but that's where my new project picks up, is resolving some of the open questions which this analog was not able to answer. And there are many. So one of the things that we did that was unique in this project was 3D print a roof, and we were able to use the overhead crane at the Johnson Space Center to lower those roof panels on top of the structure itself. It did not need to be pressurized, which is a whole other story. James mentioned earlier the challenges of creating a pressurized environment within an analog. So that was not a requirement for NASA, and it was not a requirement for how we constructed this. And again, is a research gap for us to continue investigating. Utilities. So this is a huge aspect of our project. We don't yet have a good way of integrating utilities and resources for air, water, etc. within autonomously constructed habitats, let alone regularly constructed habitats. Repair and maintainability of these systems is going to be absolutely paramount. This came up in the CHIPIA analog. They had to repair the toilet. They didn't have a good way how, and the construction of the analog itself was not well suited for those kinds of repairs and those kinds of inspections and maintenance. So that's a huge gap right there. This we've already seen. And so the interfaces, quote unquote, that you see here that I've sort of circled in blue, these are the openings that were created within the habitat to allow for entrance into an airlock. And that airlock led to a sandbox outside of the habitat where the crew was able to do simulated EVA studies. Basically, we need better answers apart from it just being a hole in the structure. And that's what we're currently developing in our upcoming project. Same for things like a material pass-through. If we're going to actually be doing geological work on regolith, we need a safe, reliable way to actually pass through materials into a lab, a pressurized area, where the crew will be to actually do that kind of work. So integration with airlocks, rovers, suit ports, materials pass-throughs, these are all things that we have open questions that we're currently addressing in our work. And these are the utilities connections for the CHIPIA analog, which connected outside the building. On Mars, we're going to have to be thinking about how we're connecting to solar power, fission potentially, and again, what other in situ resources we need to utilize and leverage to ensure that the habitat is operational. And those interfaces are the topic of my current work. And I would be super happy to talk about this if this is of interest to you and take any questions. Thank you.